Hello, welcome to the NPTEL course Fundamentals of Composite and Cellular Materials. In the last few lectures, we have been learning about the different processing techniques of metal forms, and in this lecture we will continue with that and conclude this section on the fabrication techniques of metal forms. In the last lecture, we discussed about two very commonly used techniques for fabricating metal forms. The first one was foaming by release of dissolved gases, and the second one was fabrication of metal forms using different space holder particles or components. In this concluding section of metal form fabrication, we will learn about four more techniques of fabricating metal forms. The first one, foaming by solid precursors made by powder compaction. Second process, investment casting using polymer forms. Third process, metal hollow sphere structures. So, we will see that these hollow sphere structures are a special type of metal form. It is a porous metal with a very regular and homogeneous structure, and the final thing that we will learn today is fabrication of foam sandwich panels. Again, these foam sandwich panels are a special case of cellular materials or cellular metals with excellent properties because of the face plates. These foam sandwich panels, they typically have a foam core with face sheets, and these actually have outstanding specific stiffness for bending and other structural applications. Among these processes, as you will see in this lecture, this foaming by solid precursor and metallic hollow sphere structures are basically powder metallurgy processes, while investment casting using polymer foam, this is a liquid metal casting process. So, the main keywords for this lecture are metal forms, solid precursors, powder compaction, investment casting, polymer forms, metallic hollow sphere and sandwich panels. So, to start with, the first technique that we will learn today is foaming by solid precursors made by powder compaction. A schematic flowchart for fabricating metal forms or porous metals using this technique is shown in this slide. As you can see, the process, as with many other processes discussed already, begins with a metal alloy powder. This can be aluminum powder or some aluminum alloy powder, which is the most commonly used, and some foaming agent. This foaming agent, as we have already learned, that titanium dihydride TiH2 is a very common foaming agent because of its ability to decompose at a low temperature and evolve hydrogen gas. So, initially an intimate and homogeneous mixture is formed between the metal alloy powder and the foaming agent, and this foaming agent amount or content is typically only a few weight%, and then this mixture is uniformly made typically in a tumbler mixer, as you can see in the first part or image part A of this slide. Subsequently, when this uniform mixture or this powder mixture has been formed, the next step, as with many other processes already discussed, is consolidation and extrusion. So, typically during this process, a very homogeneous and very a preform is fabricated by applying some pressure, and then these parts or these formed parts is actually put into the container for which the foam shape has to be determined. And finally, this process, this is taken to a high temperature very close to the melting point of the alloy, and during this process titanium dihydride decomposes. It releases hydrogen gas, which actually acts as the pore former, and this metal foam, it expands and fill the mold, and we obtain a very homogeneous pore distribution or pore structure as is being shown in this schematic image. So, basic description of the process is mentioned over here. So, as you can see, apart from titanium dihydride, which is the most commonly used foaming agent for aluminum and its alloys, but titanium dihydride has some issues. It is often deemed to be dangerous to use, and that is why many other foaming agents like calcium carbonate has also been used. Calcium carbonate, if it is used, if it is decomposing, then it forms calcium oxide and carbon dioxide, and the carbon dioxide is actually acting as the foam forming agent or the foaming agent in that case. This uniaxial pressing is very important, because that actually allows to densify the powders sufficiently, because if the densification is not sufficient, then the foaming gas or the pore forming gas, when it is emitted, it can easily get out of the preform, and then the foam will not be formed to sufficiently good quality, and that is why the initial applied pressure is very important. Now, if titanium dihydride is used for foaming of aluminum and its alloys, there are some difficulties involved. The first thing is that, as we know, that the melting point of aluminum is around 660 degrees Celsius, whereas the decomposition temperature of titanium dihydride initiates already at a low value of around 400 degrees Celsius. So, that is the reason that because of this large difference in the melting point of aluminum and the decomposition temperature of titanium dihydride, there may be significant loss of the gas, and also the pore morphology can actually be not spherical. To overcome that, actually there are many things or many solutions have been proposed. One proposal is that we use a lower melting alloy, that means not pure aluminum, rather than some aluminum alloy with a lower melting point can be used, and in that way that this difference in the melting point of the alloy and decomposition of titanium dihydride can be actually overcome. Another possibility is that this titanium dihydride can actually be oxidized on the surface to actually form a surface layer of titanium oxide, and that will actually also reduce or kind of reduce the this initial decomposition of titanium dihydride, and that way the foams can also be of sufficiently good quality. There is also another process that has been kind of quite a new development, that is that this powder, all these metal powders, they have some dissolved gases on the surface, that means, and then when these powders are heated to high temperature, then these dissolved or the surface coatings, they actually release the gases, and if these gases can actually be entrapped inside the foam, then actually we can automatically obtain a high amount of porosity without using any foaming agent at all. And in this case has actually been used for different powders or different cases. For example, aluminum magnesium powders have already been fabricated to form foams without any foaming agent. So, as you can see in this slide, we show here typical metal foams which have been fabricated using either the photos on the back side there of the foam using titanium dihydride, and the front side where you see the pore structures are much finer, these have actually been formed without any foaming agent and only using the intrinsic aluminum magnesium alloy as the foam forming alloy and the blowing agent. The second process that we will learn today is the investment casting using polymer foams. So, the first process that we learned until now, that was about powder metallurgy process, where aluminum alloy and some blowing agent like titanium dihydride was mixed together, and in this case it is a melting casting alloy or a melting casting process, where the initial preform is the polymer foam. So, this process is very much similar to the replica template which was used initially for fabricating porous ceramic materials. So, as you can see over here, the starting material is always a polymer foam, and the polymer foam has to be open cell in nature. It is very important that the polymer foam which is used as a precursor, it should be open cell in nature, because the idea is that initially this polymer foam is actually impregnated with a ceramic slurry. So, because polymer foams, as we know, they are not stable at a high temperature at the melting point of metal, because even if we are using low melting metal like aluminum, no polymer will sustain such high temperature, and that is why we need to impregnate the polymer foam with a ceramic slurry. The ceramic slurry can be anything, like even simple plaster of Paris or plaster can be used as the impregnating material. So, initially a slurry is made, that means this plaster or calcium or mullite or any other resin or calcium carbonate etc., they can be actually made into a slurry, and then this polymer foam is dipped in the slurry and it is pressed, so that the polymer foam absorbs the ceramic slurry, and then this ceramic slurry is allowed to cure. That means, as we know that when plaster after infiltration or after filling, if it is just maintained at kind of left at room temperature, then plaster will solidify, and then after solidification it is actually heated to a intermediate temperature. During this intermediate temperature heating, the polymer foam which is between the plaster, that means the plaster has now filled up the pores inside the open cell polymer foam, and now if we heat this up to an intermediate temperature, the polymer foam will decompose, and that will actually give rise to the pores or interconnecting pores between the plasters. Now, it is very important that these interconnecting pores are extremely important, because if the pores are not interconnecting, then the metal will not be able to infiltrate between them and it will not be forming a proper foam, and that is why it is very important that the initial polymer foam that we take for this purpose, it has high amount of open porosity. If the polymer foam does not have inherently high amount of open porosity, the open porosity has to be induced in these foams. So, after we obtain this, after the burnout stage where the polymer foam has been burnt out, we actually obtain a porous plaster, a porous ceramic or plaster scaffold, and these pores actually replicate the initial polymer or polymer struts or polymer arms between which the plaster has been impregnated. And in the next stage, which is been shown by stage C over here, this molten metal. So, now the next task is that these pores which are between the plaster, these plasters, these pores have to be infiltrated, and very often this infiltration is not an easy task, because the polymer struts or the polymer cells, they have a very fine dimension, and it is not always easy to infiltrate those things, because it is filled with air, and that is why, as we discussed yesterday, the first step always is that very often this porous plaster scaffold is put under vacuum, so that all the air is sucked out from the pores, and then the molten metal is poured on top of the plaster and some applied gas pressure is applied. Under this applied gas pressure, and because the plaster is now evacuated, the molten metal can easily infiltrate between the inside the pores, and we obtain a porous scaffold filled with the molten metal, which after solidification gives the solid metal. So, now the plaster remains there as the solid as it is, and the metal has infiltrated. So, the next and the final step is that by mechanical force, it can be some forced water jet or some light hammering, the plasters are actually removed. That means the plasters the plasters break out and they actually remove, and we actually obtain a very nice homogeneous pore structure or metal foam structure, where the metal foams or the strut dimensions and the strut structure, they actually replicate the initial polymer foam dimensions and the polymer foam struts. So, this is a very common process for fabricating open cell metal foams, and these foams have very high amount of porosity and it is predominantly open porosity, and this is commonly used, as we know, for many functional applications, especially for sound absorption or also for heat transfer applications. Now, this process which has been discussed until now, it might have some difficulties involved. The first difficulty that could arise is that achieving a complete filling of the filaments. That means, as I mentioned, the first process in this manufacturing route is the filling of the pores of the initial polymer foam with the plaster slurry, and this might be difficult because again the pores are very small in form and the pores are also filled with air. So, there might be small bubbles remaining which are not filled with the plaster slurry properly, and those unfilled regions will actually give rise to defects in the final foam structure. Second thing is that controlling the usually directional solidification and also the final process of removing the mold material without damaging the fine structure is also a difficult process, because as we know, or as I have already mentioned, these foams, the final metal foams, have very thin struts and they are very fragile actually. That means, even a small amount of mechanical force can actually damage the foam structure. That means, as we know, after the foam has been fabricated, the plaster has to be removed from between the struts, and in that situation, if the force applied is too high, that can actually damage the metal foam. Now, this process has been commonly has been used for many years by one company, ERG in Oakland, USA, and the foam that they actually market is named Duocell, and it is a very successful material which has been used for many applications. And as you can see, the pore size can actually be varied over a wide range because it depends upon the initial polymer foam dimensions, right, and this pore size can be varied like up to from 5 ppi. So, ppi means pores per inch. You will learn about this pores per inch concept in the future lectures. So, it can be varied over a wide range depending upon the pore dimensions. But one important thing to remember here is that the porosities that typically we obtain in this process is actually very high. That means, if we want to fabricate a porous foam or an open cell porous foam with a lower amount of porosity like around 40-50%, then this process is not a good choice, because if the porosity is low, that means it will be very difficult to infiltrate the initial polymer foam with the ceramic slurry. So, for this process to be successful, the porosity has to be very high, around 80 to 97%. That again takes us to the sacrificial process or sacrificial pore forming process. That means, we have to choose between the amount of porosity. That means, if we need a foam with a low amount of porosity around 40-50%, then we should go for the sacrificial pore formers, and if we want to go for materials or foams with a high amount of porosity more than 80%, where the sacrificial pore formers have very low strength, we should actually go for this process of using a replica template. So, after this, so as you can see here, this is the typical pore structure and typical macroscopic samples which have been fabricated using this process, and the left hand side image actually shows a typical 3-dimensional interconnecting pore structure, and as you can see, it is a very nice ceramic this metal struts, and it is a very homogeneous and uniform distribution, and the pore size are very well controlled. So, after this, the next process for metallic foam fabrication or porous metal fabrication that we learn is metallic hollow sphere structures. So, these are actually very unique structures, and these are actually not the conventional foams that we have learned so far. These are very unique structures also fabricated using the powder metallurgy route. So, this process has the advantage that, as you will see afterward, that this actually renders the pore structure to be very uniform. The pore structure can be absolutely controlled, which is a big advantage, because so far whatever processes we have learned for metal foam fabrication, in many of the processes the pore structure was not controlled from the beginning. That means, the pore structure depended upon the various process parameters, but in this process actually allows us to actually fabricate the porous metals with a very well defined and controlled porosity and pore morphology. Another important step, another important advantage of this process is that so far whatever processes we have learned, those were mainly limited to light metals like aluminum and magnesium, because we had to control many factors, and also the pore forming agents typically used like titanium dihydride, they used to decompose at a low temperature, and that is why those processes were limited to low melting metals or light metals like copper or like aluminum and magnesium. However, this is one technique which can actually be used for fabricating also any kind of metal, like even super alloys or copper, nickel, stainless steel. All these materials can easily be fabricated into a cellular or porous metal structure using this process. And also the porosity and pore morphology can be varied over a wide range, and also the pore size can be varied over a range from around 1 millimeter to around 7 to 8 millimeter, and also the wall thickness can also be controlled over a wide range. So, the basic flow chart for fabricating the porous metals or metallic hollow sphere structures is shown in this slide. So, as you can see, the process starts with styrofoam spheres. So, these styrofoam spheres are easily available in the market, and these styrofoam spheres are actually first coated with the metal foam with the metal powder and binder suspension. That means, initially a suspension is created with the metal powder and some binder, and then this metal powder and suspension binder is actually coated on the styrofoam spheres. And then after these spheres have been coated with the binder, with the metal powder binder suspension, these green spheres are obtained, and then these green spheres are initially undergoing shaping process, where they are actually put into the final form, and the final step is the sintering and debinding. During the debinding process, the metal this styrofoam, because they have a low melting point, the styrofoams decompose, and that actually give rise to the pores between the inside the spheres, and then these powders or this shaped body is actually heated to a high temperature where sintering takes place, and during this sintering process, neck formation occurs between the individual metal particles, and also these individual metal spheres or these coated spheres, neck also formed between them, and that actually provides sufficient strength and rigidity to the whole foam structure or the whole porous metal structure. So, as you can see over here, this slide actually shows, the right hand side actually shows a typical metal foam structure or this porous metal structure fabricated using this hollow sphere technique. And when this structure is actually compressed, as you can see from the on the left hand side, this homogeneous compressed body is obtained, and again during compression this actually absorbs a huge amount of energy, and this is again very good for energy absorption applications. So, as I already mentioned, this typical feature of this unique cellular structure has many advantages. One of the advantages, as I already mentioned, is that the pore morphology and the pore size is very easily controlled, and they are actually very much well defined because they depend upon the initial size and dimensions of the styrofoam spheres. Another important thing is that these materials or these kind of porous materials have a very different amount or different degrees of porosity. That means, these structures typically contain both open and closed porosity. So, typical microstructures of these foams or these open porous of these cellular solids fabricated by these hollow sphere structures, these typical microstructures are shown over here. So, as you can see over here, these this left hand side image is actually showing a triple point junction where three spheres actually contact each other. So, as you can see over here, this was actually boundary of an initial form of an initial. So, this is part of an initial sphere, as you can see over here, and this is this triangular region that you see in the middle. This is typically the point where three such spheres have joined together. That means you have closed porosity in these regions. That means these regions between the individual spheres, they actually form the closed porosity, whereas these regions, that means between the individual spheres, these triangular regions, which is these regions, these are actually open porosity, because these are actually interconnected. And then because these powder materials or individual powders are actually sintered together, that is why you see all those black portions or black features inside the cell walls, and they are actually all the micropores which have not sintered properly. That means you have here three levels of porosity. You have the macropores within the spheres, which are the closed pores. Then you have the open pores between the triangular, between the joining of the individual spheres, and then you have the very small micron sized pores or micropores, which are between the cell or within the cell walls, remaining because of the lack of sintering between the individual metal particles during the final sintering process. And if such a foam is sectioned in the kind of along the vertical direction, you get typical structures like this, where you can see again the pore structure is very uniform. And then if this structure is compressed along the vertical direction, as I already mentioned, that these structures are extremely good for energy absorbing applications, and you can see how the deformation actually propagates at different levels of strain. And this deformation procedure or deformation mechanism of these structures will be discussed in some of the future lectures. So, this brings us to the last technique for fabricating cellular solids. It is again a special kind of cellular material. It is called foam sandwich panels, or very often it is called aluminum foam sandwich panels, or AFS panels, because these are the most commonly used, and these have many practical applications like in automobile applications or aerospace applications, because as we already mentioned in the previous lectures on material selection, these sandwich panels have extremely high specific properties, especially specific stiffness in bending. So, these are typically fabricated by so we have these face sheets, that means the aluminum or dense face sheets are there, and these are actually roll clad or roll bonded to a foam core precursor. That means there is a precursor, powder precursor, and this precursor is foamable. That means we again use some kind of a powder mixture of aluminum powder and titanium dihydride foaming agent or whatever, and then this powder precursor is actually kind of roll clad between two face sheets. That means you have one face sheets and this is another face sheets, and then in between actually you have this powder mixture of the metal powder and the foaming agent. Then this is kind of bonded together by roll cladding and roll bonding, and then if this thing is actually heated to a high temperature for foaming to occur, then this titanium dihydride or the foaming agent will decompose, and that will form the pores inside the structure, and finally you obtain such very unique structures where you can see that the outer surface is the face sheets, which are actually these solid face sheets, and then inside you have a very nice and homogeneous pore morphology and pore structure, and these actually provide extremely good properties at a very low density. So, with this I come to the end of our discussion on metal foam fabrication. We have discussed in the last 3 lectures on several techniques, around 8 techniques we learned about various metal foam fabrications, and we saw that depending upon our requirement and what kind of porosity and pore morphology we want, we can use either powder metallurgy route or melting casting route to fabricate different kinds of metal foams. To conclude today's lecture, we learned about various processes. We learned that solid precursors of aluminum powder or some metal powder and some foaming agent like titanium dihydride or zirconium dihydride or calcium carbonate can actually be blended together, and then after blowing we can actually obtain very nice porous structures. If we want to have porosities or open porosities more than 80%, like in the range of 80 to 95%, then we learned that a very useful technique is the replica process, or which is also called investment casting process, which is starting with a polymer foam, and this polymer foam is actually impregnated with some slurry containing a stable material like plaster, and after the removal and infiltration of the metal inside the porous plaster body, we obtain a very nice homogeneous open foam structure. And also we learnt about the hollow sphere structures, where individual hollow spheres are sintered together to obtain a very nice homogeneous and reproducible pore morphology and foam properties. So, the references used for this lecture are provided over here, and in the next lecture we will learn about the polymer foams, their processing and properties, and also some techniques for fabricating polymer foams. So, with this we come to the end of today's lecture. Thank you very much.